Alright, in this video, we study various properties of matrix determinants. We can exploit these properties to simplify, sometimes greatly simplify, the computation of matrix determinants. So let's start. To begin with, let's define the notion of linearity. Okay, so first, let V and W be vector spaces. And F be a map from V to W. Okay, we say this F is linear, is a linear map, if the following two conditions are satisfied. That is, first, for all U and V vectors in the domain, we have f of u plus v is equal to f of u plus f of v. Okay, so the sum is mapped to the sum. And two, for all vector u in the vector space v and lambda in the scalar lambda in the scalar set, we have f of lambda u is equal to lambda times f of u. Okay, so this scalar multiplication is preserved. Okay, and these two conditions can be summarized as follows. So u and v are vectors, and lambda and mu are scalars. Okay. And f of lambda u plus mu v is split into lambda times f of u plus mu times f of v. So this property is called a linearity. You should check if these conditions are satisfied for any linear function. For example, let's say f of x is equal to ax, okay, where x is any real number and a is a real number. Okay, so in this case, if we add x1 plus x2, then that is ax1 plus ax2. So if we split this, x1 plus ax2, but this is equal to this is equal to f of x1, right? This is f of x1, and this is f of x2. And similarly, f of lambda x is equal to f of according to the definition of this function, that's a lambda x, and that is lambda times ax, which is lambda times f of x. So this function is indeed linear. Next, we show that determinant is a sort of linear function. So to see this, let's consider a matrix as a column vector of row vectors. Okay, so if we have a11, a12, and so on, a1n and a21 and so on, and up to an1 and an. So this is n by n matrix, and we consider this as a column vector of row vectors. So this row is considered as a row vector a1, and the second row is considered as a2, another vector, a1, a2, and so on up to an. So let's consider a matrix in this way. Then we have the following property. Okay, a1, a2, and so on, and Let's say at ith row we have bi plus ci, okay, and an. So except for the ith row, so ith row, except for the ith row, everything is like a vector. And ith row is made of the sum of two vectors. Okay, in this case, this a determinant of this matrix, let's say consider determinant of this matrix, is the sum of determinants. And bi and so on, an, determinant of this matrix, and the determinant of a2 and ci and this matrix. Okay, so here we consider the determinant as a function of a vector or in the ith row. Okay, so this is a function. So let's call this det. Let's call this function det. Det is a function from n-dimensional vector space to one-dimensional vector space. The result is the determinant, so it's a real number. And here we consider determinant as a function of its ith row. Okay, so ith row is made of n real numbers, so it can be considered as a n-dimensional vector space. So determinant is considered as a function from this space to real numbers. Okay, if we consider that this way, then it's a linear function. Okay, so first we have this. The sum here is split into two parts. And also, if we have determinant like this, a1, a2, and so on, the ith row is multiplied by lambda. Okay, and this is equal to lambda times the determinant of a1, a2, and so on, ai, and an. Okay, so these two conditions are met, so we can say that determinant construed this way is a linear function. And of course, this ith row, this I can be arbitrary. So it can be the first row, second row, or any rows. So for any row, this linearity holds. So in this sense, it is determinant is considered as a function of all these vectors. So n vectors, and for each of these vectors, the linearity condition holds. So we say determinant is multilinear in this sense. Okay, so let's prove this. And first, bi plus ci, so row vectors, is something like this: b1 plus c1, and b2 plus c2, and so on, and bn plus cn, right? Okay, so if we calculate the determinant of this matrix, bi ci and an, of course each of these is a vector, and we focus on this row, then the determinant is given as j from 1 to n and negative 1, I plus j, and bi plus ci, and the smaller matrix determinant, aij. So this is the matrix obtained by removing the ith row and the jth column of this whole matrix. Okay, but this is a real number. It's just a simple real number, so we can split this summation. So by using the distributive law, we have j n negative I plus bi, and aij. And another sum, j and ci and aij. But this is the determinant of this matrix A1, A2, and so on, and bi, wait a minute, yeah, bi and an. And this is the matrix of this, this is the determinant of this matrix A1, A2, and so on, and ci and an. Therefore, it's proved. And this one is also easy to prove. So the determinant of this matrix, lambda ai, an. So focus on the ith row again. Then the determinant is given as this. -1 to the power of I plus j, and we have lambda a I j here, and the smaller determinant aij. But this is just multiplication between real numbers, so we can take this lambda out of the summation, and then we have this aij and aij. But this part is just the determinant of this matrix, A1, A2, and so on, AI, and so on, AN. So we're done. Okay, next property is called antisymmetry of determinant. The reason why it's called antisymmetry is obvious, as I explained it. So if we have a matrix, determinant of a matrix, A1, A2, so again, we see a matrix as a column vector of row vectors. So let's say if we have ith row here, and somewhere we have I prime row, I prime, okay, and an. If we swap two rows, then the result is the negative of the original matrix. Okay, so if we swap I and I prime here, A1, A2, and so on, and I prime here, and I here, then the result is negated. Okay, so this comes here and this comes here. So we swap the rows. Then we get the same result except for the sign. Okay, and for this reason, if these two rows happen to be the same rows, okay, happen to be the same vector, that is, if we have something like A1 and B and yet another row, the same vector, and this determinant is 0. Why? If we accept this fact, then if we swap these two rows, then we still have the same determinant, right? But its sign is negated. So this is equal to the same vector, same determinant. So this cannot hold unless this determinant is 0. So a is equal to negative a, then that means a is equal to 0. So something like that. So in this sense, it's obvious that this determinant is 0. Okay, so let's prove this one, and we prove by mathematical induction. Okay, so when the matrix size is 1 by 1, nothing to be proved. So consider 2 by 2 matrix. Okay, nothing to prove because we need multiple rows to swap. If there is only one row, then we cannot swap. So in case of 2 by 2, so A, B, C, D. So the determinant is AD minus BC. So if we swap these two rows, then we have C, D, A, B. So the determinant of this is CB minus AD. So BC minus AD, which is the negative of the first matrix ABCD, the first matrix determinant. So in case of 2 by 2 matrices, the claim is true. Next, suppose the claim holds for any m by m matrices. And consider m plus 1 times m plus 1 matrix A. Okay. And also consider another m by m matrix, m plus 1 by m plus 1 matrix B, where A, which is equal to A, matrix A, this one, with rows K and L are swapped. Okay, so if we have A as A1 and so on, and a kth row and lth row, an m plus 1, okay, so if we have this determinant, then the determinant of B is something like A1 and so on, and AL and AK and AM plus 1. So this is kth row and this is lth row, and if we swap them, then AL appears in B at the kth row, and lth row we have AK. Yeah, okay, so this comes here and this comes here, so we swap, and we show that the determinant of B is negative of the determinant of A. Now let's try to calculate the determinant A, and according to the definition, this is something like this: J equal to 1 to m plus 1 and negative 1 to the power of I plus j. Here we need to fix this I, okay, and we can assume that since we can choose any rows, we choose some row that are different from K or L. So this I is not equal to K or L, okay? And Aij and the smaller matrix, okay? Here, this Aij, capital Aij, is a m by m matrix, right? Because this is obtained by removing the ith row and the jth column. So it has one less rows and one less columns. So it's an m by m matrix. On the other hand, the determinant of B is something like this. Okay, since B, the matrix B is the same as A, except except that the kth row and the lth row are swapped. So we have something like this: J and let's call it Bij and Bij. Okay, and of course this Bij is also m by m matrix. Okay, However, we are choosing I, so we are using same I here. This I and this I are the same I's. Since I is different from K and L, so everything in A matrix A and matrix B are the same. Okay. So in this ith row, this Aij and Bij, they are actually the same elements. So this is actually Aij. And the swapped rows, K and L, are actually included in this smaller matrices. Okay, and of course they are almost identical matrices except for the kth row and the lth row. Actually, it's not K and L, but those rows that correspond to the kth row, kth and lth rows in the original matrices. So that means, according to the induction hypothesis, we have the determinant of Aij is equal to negative of the determinant of Bij, right? So if we substitute, let's substitute this into here, then we have determinant of A is equal to negative of, wait a minute, negative of determinant of negative 1I plus j of Bij. Okay, so this negative sign appears and Aij here. And this is equal to negative of the determinant. So this thing is the same thing as this thing. So this is the determinant of B. And we are done. And similarly, actually, we can show that if we swap two columns instead of two rows, we also have the same result. That is, if we swap two columns, the determinant is negated. So this property is called antisymmetry of determinants. Okay, now let's consider this 3 by 3 matrix, and we again consider this matrix as a column vector of row vectors. Okay, row vectors are x1, x2, and x3. Now, let's define 3 orthogonal bases set. So E1, 1, 0, 0. So this is a vector, and another vector 0, 1, 0, and another vector 0, 0, 1. So let's express x1, x2, and x3 in terms of these 3 vectors. Okay, for example, x1 is x11, x12, and x13. So this can be split into sum of 3 vectors, x11, 0, 0, and 0, x12, 0, and 0, 0, x13. And also, each of these can be split into the scalar multiplication of these unit vectors. So x11 times 1, 0, 0, and x12 times 0, 1, 0, and x13 times 0, 0, 1. So this x1, this vector x1 can be expressed as a linear combination of E1 and E2 and E3. And the coefficients are x1, x11, x12, and x13. Now, using these such expressions, let's simplify the determinant of this matrix X. So the determinant of this matrix can be written as this: x11, E1, and x12, E2, and x13, E3, x21, E1, and x22, E2, and x23, E3. x31 E1, x32 E2, and x33 E3. Now let's apply all the rules we have learned so far. First of all, let's focus on the first row. Okay, this is a sum of three vectors, and as we have learned that this determinant considered as a function of this row vector in the first row, it's a linear function. So this can be split into the sum of determinants, right? So if we do that, we have this. Let's see, E1, and the rest stays the same. So let's copy and paste. Copy and paste. Okay. So we have this plus x1, 2, and E2, and paste this thing, and x1, 3, and E3, and paste. Same thing. Okay, so we have this decomposition. And we can apply the same thing to the second row of the first term, and the second row of the second term, and the second row of the third term. And again, after that, we do the same thing for the third row. In the end, what we obtain is something like this. So after all the expansion, what we have is this. So we have, again, all the permutations of three numbers, 1, 2, 3. So this is 1, 2, 3, and 1, 3, 2, 2, 3, 1, 2, 1, 3, 3, 1, 2, and 3, 2, 1. So by using linearity, we can reach up to this point. Now, what's remaining is the computation of these determinants. Okay, but these determinants can be calculated by swapping these rows. Okay, but first of all, let's consider this one, 1, 2, 3. Okay, so that is, so if you expand this 1, 2, 3 using their components, this is the determinant of the identity matrix 0, 0, 1. So if you calculate this, this is equal to 1. Okay. So for example, let's consider this one, 1, 3, 2. Okay, E1, E2, 1, 3, 2. Okay, E1, E3, E2. Okay, so if we swap the third and the second rows, then we have negative E1, E2, E3. And we know that the determinant of this matrix is 1, so that is negative 1. Okay, so this reduces to 1, and this reduces to negative 1. And similarly, this one, 2, 3, 1. Okay, consider E2, E3, and E1. So first we swap 1 and 2 here. So E1, E3, and E2. Okay, so that introduces one negative sign. And next we swap this 3 and 2. Okay, then it swaps again the sign, so that becomes positive. E1, E2, and E3. And this is equal to 1. So for this one, we have positive 1. Excuse me, positive 1. And similarly, this one, we can obtain 1, 2, 3 by swapping these two only once, so that will be negative 1. And this one, once 3 and 2, wait a minute. So this can be arranged into 1, 2, 3 by two-step. two steps. So that will be positive 1. And this one will be 1 and 2. So only one swap. So that is negative 1. So in this way, we can find the determinant of a complicated matrix. So applying the properties like linearity and antisymmetry, we can reduce a complicated matrix determinants into a simplified form. Okay, next we prove the following interesting property. That is, the determinant of a product of matrices is the product of determinants. So if we have two n by n matrices, x and y, and try to calculate the determinant of their products, xy, then the result is the same as we calculate the determinant of x and the determinant of y and multiply them. So that is the determinant of xy. Okay, so let's prove this. First of all, calculate the ij component of the product xy. So according to the definition of matrix multiplication, it's something like this. So x, let's say we have xij for the matrix element x of x, xik, and ykj here. But look at this one. This is the element of matrix y at the kth row and jth column. Okay, so this can be also written as xik times the row vector, the kth row vector of matrix y, and its jth component. Okay, so this one is the kth row of y. Okay, so because of this, the matrix determinant of xy can be written as this: x11 and y1, the first row, and x12 and y, the second row, and x1n and the nth row of y, and so on. So x21, y1, x22, y2. So this is quite similar to the decomposition we tried for this matrix, like this, 3 by 3 matrix. So something like this. Instead of E1, E2, E3, we are using Y1, Y2, Y3, and so on. To n, yn. Okay, so again, using the linearity of matrix determinants, this can be expanded into the sum of linear combination, kind of linear combination of determinants. So that we write as this. So sum over sigma, the meaning of this I will explain later. And x1 sigma 1 and x2 sigma 2 and so on, and xn and sigma n, and the determinant of y sigma 1, y sigma 2, and y sigma n. Okay, here sigma means permutation of numbers. So sigma means permutation of n numbers, 1, 2, 3, to up to n. Okay, and sum is all possible permutations of n numbers. Okay, so this is like x1, 2, or x2, 3, and so on. Okay, so sigma 1, this sigma 1 is the same as this sigma 1. So this is one of these n numbers. Okay, and this sigma 2 is another number out of these n numbers, and so on. So this summation is exactly like the summation we obtained here for 3 by 3 case. So permutation is like this. In this case, permutation sigma 1 is 1, sigma 2 is 2, sigma 3 is 3. In this case, sigma 1 is 1, sigma 2 is 3, sigma 3 is 2. So sigma something is permutation of these numbers. Okay, at this point, we apply the anti-symmetry of determinants. Okay, so if we swap two rows in this determinant, then the sign is negated. Okay, we have an opposite sign. And if we swap it twice, then the sign is again reverted, so it becomes positive again. And 3 times negative. So odd numbers times of swaps becomes gives negative sign, and even numbers of swaps doesn't change the sign. Okay, by changing this, we have either positive or negative, and that is represented by sign of sigma. Okay, so if it requires even number of swaps to recover the original order of 1, 2, 3, and so on, then the sign is, so odd number, then sign is negative. Even number, sign is positive. Okay, so this is something like this, sign of sigmas. So this sign is actually a universal property of a permutation. So there are multiple ways to recover the original order, but the sign doesn't change. Okay. Okay, so x1 sigma 1 and so on, and xn sigma n. And now we have this order, y1, y2, and so on, yn. Okay. So by swapping this, the sign may change, and that is expressed by this function, sign function. Now look at this. This determinant, it doesn't include sigma anymore. So this is a constant with respect to permutation sigma. So, and this part is the determinant of y, right? So it's the determinant of y. So all we are left to do is to show that this part is the determinant of x. So is this really equal to this determinant of x? So let's show that. Okay, to begin with, first note that this determinant, e1, e2, and so on, en. So each of these vectors is the unit vector, the orthogonal basis vector. So e1 is something like this. So the first element is 1, and everything is 0. And e2, the second component is 1, and everything else is 0. And ei, the ith component is 1, and everything else is 0. Okay. So by using this, this matrix is actually the identity matrix. So 1, 0, 0, and the diagonal elements are all 1, and everything else is 0. And you can check that the determinant of this identity matrix, any identity matrix, is actually 1. Okay. So multiplying 1 doesn't change anything. So let's multiply 1 to this thing, sigma, and sine of sigma, and x1 sigma 1, and so on, and xn sigma n times this thing, okay, e1 and en. Now, this times this can be also expressed as this matrix, the rows are permutated according to sigma, sigma n. So E sigma 1 and so on, and E sigma n. Okay, so if we swap the rows of this matrix according to this permutation sigma, then we get the sign of sine sigma. But that is already here, so we can get rid of this function by permutating the rows of this matrix, which gives us this one. Okay, but this thing is actually what we obtain from this x11 e1, x12 e2, and so on, x1n en, and x21 e1, x22 e2, and x2n en, and so on, and xn1 e1 plus, and so on, and xnn en. Right? To see that, just again apply the linearity of determinants, and what you get is this one. So apply the linearity of determinant to this one, and you get this. So they are equal. But this thing is actually the determinant of x. So as we wanted to claim, this part is indeed equal to the determinant of x. Therefore, the determinant of the product or between x and y is the product of the determinants of x and y. So in the end, we have the determinant of xy is equal to determinant of x times determinant of y. And we are done. Okay, yet another property we give without proof is that the determinant of the transpose of matrix is the same as the determinant of the matrix. Okay, we don't prove it. If you want to prove it, do it. Next, we like to find a general way to derive the inverse matrix of a given matrix. But before that, let us define something called adjugate matrix. Adjugate matrix. Okay, so let A be a matrix, n by n matrix. Okay, and its adjugate is here we denote by this A star is defined as this. Its elements are Aij star, and Aij star for given matrix A is defined as this. So negative 1 to the power of I plus j, so this I and j are here, the index. And the matrix, the smaller matrix we obtain when we calculate the determinant of A. So this is, note this transposed elements indexes. So it's not ij but ji. So this is the matrix obtained by removing the jth row and the ith column of the original matrix. Okay, so a matrix made of such elements is called the adjugate matrix of this matrix, given matrix. So in case of 2 by 2 matrix, A, B, C, D, let's call it A, and its adjugate is, so what is it? So it's one element of this adjugate should be, let's say, one element is something like this. So A11, okay? So A11 is this. So that is just D, right? So the 1 1 element is D, and 1 2 element is something like 1 plus 1 2 element, and 2 1 here. So A 2 1 means the matrix obtained by removing that second row and the first column. So that is B. Okay, so that is negative B. And similarly, 2 1 element is negative 1, 2 plus 1, and A 1 2. So that is the matrix obtained by removing the first row and the second column. So that is C in this case. And the negative sign here is here. And this element is negative 1, 2, 2 element. And 2, 2 element is A. So that is A. So that is the aggregate matrix of this 2 by 2 matrix. If you remember, the inverse matrix of this 2 by 2 matrix was given by this. A inverse is 1 over the determinant, AD minus BC, and the aggregate. So this aggregate matrix is an important component of the general inverse matrix of general sizes. So you can guess from here, for general n by n matrix, the inverse matrix, if it exists, it's given by something like this. Okay? And we'll see, and this is indeed the case. Okay, so now let's prove some theorem. Let A be a matrix made of these elements, n by n matrix. Then, and also A star is the aggregate of A. Aggregate of A. Then we have the following properties. Okay, A times A star is equal to A star times A is equal to determinant of A times the identity matrix. Okay, and 2, A has a right inverse. If and only if determinant of A is non-zero. Okay, so IFF means if and only if. Okay, if and only if. So that means has a right inverse is equivalent to determinant is non-zero. By the way, right inverse means this. A and right inverse, let's write it as B, is equal to this. So if A is given, and if B is some matrix, square matrix of the same size, and if you multiply A by B from the right, then the result is the identity matrix. In this case, it's n-dimensional. So in that case, B is said to be a right inverse of A. Okay, so there exists such B inverse if and only if the determinant of A is non-zero. And 3, if A has a right inverse, then inverse, let's call it X. Okay, instead of B, we call it X, and then X is also a left inverse of A. So what that means is this. If AX is equal to the identity matrix, then XA is equal to the identity matrix. So if X is multiplied to A from the left, the result is the identity matrix. In that case, we call X a left inverse of A. Okay. So that means if there is an inverse, that is all right inverse, it's also left inverse, and vice versa. If there's inverse, it's inverse from both sides. Okay, so let's prove this, and first let's prove this one. Okay. So let's write z as a times a star, and the element of z is zij. Okay, so zij is given by this k equal to 1 to n, and aik and a star kj. Okay, but a star is the adjugate of a, so applying the definition of the adjugate, we have ak and negative 1 and k plus j, and what was it? Smaller matrix, and j with kj, so it's jk, right? Okay, so let's arrange a little bit. So this looks almost like the definition of the determinant of some matrix. So kj, jk, okay, and aik and ajk here. So if I is equal to j, then what we have is this. Zii is equal to k. So j is I, and aik and aik. So j is equal to I, right? So this is the definition of a matrix determinant. So this is actually equal to the determinant of A, right? And okay, so that's fine. And if I is not equal to j, then what happens? So we have this, and I and j are different, but this is the determinant of a matrix where the ith row and the jth row are the same, right? So just, I and j are fixed here, so just write this as like bjk, and then it's a matrix determinant where the jth row is this, but it happens to be the same as the ith row. So in that case, that must be equal to 0 because there are two same rows, and for such a matrix, the determinant is 0, as we have learned before. Therefore, to summarize these two cases, Zij can be written as the determinant of A times Kronecker's delta. Remember Kronecker's delta? This takes the value of 1 if I and j are the same, and otherwise it's 0. So in other words, the matrix Z, so this is the element of the identity matrix. So in other words, this is the determinant times the identity matrix. Therefore, we have proved A times A star is equal to this. And you can also prove A star times A is equal to the identity matrix in a similar manner, which we skip. Okay, and the second point, it says if A has a right inverse, then determinant is non-zero. And if determinant is non-zero, then A has a right inverse because it's if and only if. So we have to prove both ways. Okay, so let's prove only if part first. So suppose A has a right inverse. Let's call it x. Then that means A times X is equal to the identity matrix. Okay, now let's take the determinant of both sides. But the determinant of the identity matrix is 1, and the determinant of the product is the product of the determinants, right? So the product of two numbers is equal to 1, which is non-zero. Therefore, the determinant of A cannot be 0. Okay. Now, let's prove if part, and suppose the determinant of A is non-zero. Okay. From part 1, we have A times A adjugate is equal to the identity matrix times the determinant of A, right? And now we're assuming this is non-zero. Therefore, if we divide both sides by, so it's non-zero, so we can divide both sides by determinant of A star is equal to the identity matrix. So if we define X to be 1 over determinant times A adjugate, then this X is the right inverse of A. Let X be this, then A times X is A times 1 over A determinant and A adjugate, and that is equal to the identity matrix. Therefore, a right inverse exists. And we are done. And part 3. Okay, so it says if the right inverse exists, then that right inverse is also a left inverse of A. So, but from part 2, okay, suppose a right inverse X exists. And by part 2, then the determinant of A is non-zero. Okay, so since X is right inverse, we have this, and if we multiply by both sides by 1 over A determinant times A star adjugate from the left, so we have 1 over this determinant A star A X equal to 1 over A determinant A star I. Okay, but this part, according to our result here, this is equal to identity matrix. And so identity matrix times any matrix is just this. And identity matrix times X is just X. So the right inverse is actually this. Okay. Now let's multiply this X to A from the left. Okay, and actually we already shown that, so since from part 1, A star A is I, right? So if we divide by, oh wait, not I, but this, and determinant of A times the identity matrix. So if now we are assuming that this determinant is non-zero, we have A and A star. A is equal to the identity matrix. So this is the left inverse, which is the same as the right inverse, right? So if the right inverse exists, that inverse is actually also a left inverse, and both of which is this. So the inverse is actually unique. So if there are two inverses, they must be the same inverse. So in that sense, for a given matrix A, its inverse is written as this. A, it looks like A to the power of 1, but it's not power, it's inverse. It means inverse. Okay. Now we know how to calculate the inverse matrix of a given matrix as long as it exists. So first we calculate the determinant and we calculate the adjugate, and then divide the adjugate by the determinant, and that's the inverse matrix. Okay, finally, let's prove this simple result. Suppose we have matrices A and B, and both of which are invertible. That means the inverse of A exists and the inverse of B exists. Okay, so A inverse and B inverse, they both exist. Then the inverse of the product also exists, and that is equal to not A inverse times B inverse, but it's B inverse times A inverse. Okay, so the left-hand side means the inverse matrix of the product matrix AB. And the right-hand side means the product of inverse matrices. So B inverse times A inverse. And B inverse is on the left, A inverse is on the right. It's, the order is opposite here. So it's easy to prove this one. In order to show that this is the inverse of AB, we just multiply. So AB times B inverse A inverse is equal to, because of the associativity of matrix product, this is same as B inverse A inverse, but since this becomes identity, and this becomes A times A inverse, and this becomes identity. So this is right inverse of AB. And we can also show that B inverse A inverse. So B inverse A inverse A B is B inverse identity, and that is so this identity will disappear, and B inverse times B is identity. So this is indeed the inverse of AB. Okay, again, I stress that this order matters, okay? It's not the same as A inverse, B inverse, because matrix multiplication is not commutative. So this is not the inverse of AB. Instead, this is actually inverse of BA. Okay, so that's all for this video, and see you later.